All right, let's take a look at the next section in the discovery of the atom. So, a few years later, after the plum pudding model gets proposed, another scientist, Rutherford, decides to put the idea of the plum pudding model to the test. Under the assumption that matter is composed of a positively charged membrane that permeates throughout the entirety of the surface of that particle or that substance, what Rutherford decides to do is shine a ray of light that has positive charge at the gold foil. And the idea is that if the gold foil indeed has a surface of positive charge throughout, the ray of light that has positive charge already ought to be deflected by the positive charge of the gold foil membrane at every point of contact. And so what's expected to happen is that you'll have these deflection rates taking place. And to give you an idea, this is roughly the way the experiment did look like. You had the source of the beam of positive charge here on the right side. The beam was shooting through the gold foil, passing through, and here's the detector, and that's another detector right here as well, just to see, different points of contact. Now the ray, just to give you an idea, the ray of light that you're passing through is actually a ray composed of helium particles that have a 2 plus charge. Now, not only is the charge higher than that of the electron, but on top of that, the mass is about 1,000 to 10,000 times greater than that of the electron. So you're dealing with a relatively massive particle with, relatively high charge. So you are expect to see some deflection. But what ends up happening is that although you do see some deflections happening, a good amount of the ray of light goes right through undeflected at all, meaning that a good chunk of the rays of positive particles, which have a massive charge, interact with nothing on their way through the gold foil. And there are certain regions where, yes, there's an interaction happening, but it's not all of it that comes to see the positive charge. And in addition, there's a very few amount of these rays that get deflected all the way 180 degrees from the point of contact, meaning that the moment they hit the gold foil, they come back exactly to the place and the trajectory they came from. So it looks like, as a result of that very drastic fact, that a good chunk of the rays are passing through undeflected. Some of them are getting deflected 180, degrees the way they came from. The only way that could happen is if there is a massive particle that contains most or all of the positive charge in the atom. But the reason that most of the particles are passing through the gold foil without any interaction whatsoever ultimately says that probably most of the atom is empty space, but you have some region of space within the atom that is very heavy and that contains most or all of the charge. So here's where the idea of a nucleus takes place. If you're going to have the majority of the positive particles present in this tiny space, the rest of it has to have basically be empty space altogether, which will explain why these rays are passing through undeflected. And so the Thomson model, the plum pudding model, is basically proven incorrect by the gold foil experiment of Rutherford. And instead, it gets refined to be thought of as follows: that there is a very small portion, a very small volume of space within the atom where the positive charge resides. And the rest of the atom is pretty much empty space, but you have the electrons surrounding the positive charge to balance out the charges. So this is the Rutherford model of the atom. Okay, and then here's Rutherford. Now, one more extra thing that he does, which is actually pretty useful, is to go after the positive charges and see what they are. And he manages to isolate one of them, and it's actually not as difficult as you would think, because as it turns out, the particles that contain the positive charge, which are now known as protons, derive directly from the hydrogen atom. So all he needed to do is just isolate H pluses, so a hydrogen atom from which its electron has been removed. And he basically does this in 1919. He provides enough energy in the form of X-rays to hydrogen, removes the electron, and then uses that as the source of protons. And This is something that we do still nowadays a lot, especially in the field of physics. We can produce a beam of protons quite easily by just applying this type of approach, providing enough energy to the hydrogen atom to knock off its electrons, and then we just direct the positively charged protons away from the electrons using magnetic fields. So he manages to do that, and he does an experiment kind of similar to the one that Thomson did, and figures out that the charge of the proton is exactly equal to the charge of the electron, except that it is positive as opposed to negative. In addition to that, he manages to get the mass of the proton and discovers that the proton mass is about 10,000 times more than that of the electron. So what this also implies is that the atom, specifically the nucleus of the atom, not only contains all the positive charge that it possesses, but it also contains the vast majority mass that the atom has. All right, now this kind of starts presenting a new picture for the periodic table, because we now know that there are protons present in the nucleus. We know that there are electrons, and so another scientist, Moseley, in 1913, starts studying the different elements by using X-ray, specifically something known as X-ray emission spectroscopy. And Moseley basically makes a very important correlation, something that shapes the way we look at the elements on the periodic table to this day still. And it is that he makes the correlation that it's the number of protons that an element possesses which ultimately dictates where those elements are aligned up in the periodic table. It's all about the protons. In essence, what he implies with this is that the number of protons the element has is ultimately what dictates what's the actual element that you're dealing with. And by doing so, he basically sets in motion the proper way of setting up the table. And this time around, the transition metals are no longer scrambled, allocated to the same cell, sharing the same cell with multiple elements. Now every single element has its own cell. And the transition metals now have their own spot in the periodic table. So that's perfect. Now there's still some elements at this point in 1913 that were missing. Element 43, technetium still missing. We have elements 85, astatine missing, 87 through 89. So you have francium, radium, actinium, protactinium, and the rest of the transuranic elements. Those are all basically radioactive elements that ultimately had to be made in nuclear reactors. But the big thing about the Moseley relationship in respect to the number of protons and the identity of the element is crucial, because that's how we look at the periodic table nowadays. We look at this number here as the superscript to the left side of the element, the atomic number of the element, to basically convey the idea of which element we're dealing with. And that's a much better way of arranging the elements as opposed to mass. Now, eventually, in 1944, that's when the rest of the elements already get artificially made in nuclear reactors. And one of the big, it's not the only person, but one of the big players at the time was Glenn T. Seaborg. Glenn T. Seaborg was a faculty member at Berkeley during this time, and during World War II, he was also very much involved in the Manhattan Project. But he's one of the people responsible with synthesizing all these elements that I had here highlighted in red, including a lot of the ones that you see here in the red column. And so Seaborg contributed so much to the synthesis of elements that he is to date the only person who has had an element, in particular element underneath tungsten, the one right here. He's the only person that has had an element named after him while he was still alive. So his contributions are that big. Alright, so now we have the proper arrangement of the atoms in the periodic table based on the number of protons that the element has. We call that the atomic number, and I'll have more to say about it a little bit later. But to finish this discussion, we start looking at the elements, and now we know, okay, so one proton corresponds to one specific element, hydrogen to be most exact. 2 protons in the element means that you have helium. 12 protons in the element means that you have magnesium. 17 you have chlorine, and 79 protons you have gold. Okay, so this is the thing. The mass of the proton is roughly speaking correlated to the atomic mass of the element, and we know that because the protons have 10,000 times more mass than the electrons, so the majority of the mass comes just from the protons. So thinking about the nucleus, right? If we have one proton, we're expected to have a mass number of 1, and that's roughly in the ballpark, 1.008. So that looks on par with what we would expect based on the number of protons. Helium, however, we have 2 protons there, so we should expect a mass of 2, and instead we have a mass of 4, twice as much. So what's going on there? In magnesium has a 12 protons altogether due to atomic mass, and yet its atomic mass ends up being twice that value. The same story with chlorine, 17 protons, and yet the mass is more than twice that value. And for gold, it gets even worse. Now we're definitely way more than twice the value of the number of protons. So something is missing. And what's actually missing is the fact that we haven't accounted for all the particles that are present in the atom. There's one more particle that we haven't yet discussed. And Chadwick is the person that makes the contribution of determining what this particle is. Due to the fact that the atomic masses are not lining up with the number of protons that the elements possess, Chadwick argues that there is yet one more particle within the atom that hasn't been caught or identified yet. And the reason why is because this particle probably doesn't have any charge. If the particle doesn't have any charge, it will not actually be affected by magnetic fields. So doing the experiments that Thomson and Rutherford did, you wouldn't see any change because they all depended on magnetic fields being present, and the elements, or rather the elementary particles, reacting to the magnetic fields. So he says, okay, so there's probably a particle that has no charge since it's not reacting to magnetic fields, that can penetrate matter as a result of not having charges, and that has probably a mass that is kind of close to that of the proton. Now the mass of this new particle, which now we know it as the neutron, plus the mass of the proton added to give you the entire mass of the element. And one experiment that he did that was very clever was shining the helium 2 plus particles, the alpha particles, to a beryllium source. And the interaction of beryllium with the alpha particles actually produce these particles known as neutrons. And because they don't have a charge, you can't really use magnetic fields to identify them. So instead, you allow them to react with other material like paraffin wax. And this interaction ultimately produces protons that can be detected. And the actual reaction, in case you're wondering, is as follows. You have helium-4 reacting with beryllium-9, forming carbon-12 and neutrons. So that's what's going on with the beryllium. Then you have a different reaction between your neutrons and paraffin wax that is made out of hydrogen and a few other elements. All right, so by doing this, being basically coming up with a way of producing the neutrons via this nuclear reaction, ultimately we can find out characteristics about the neutron. The charge is indeed 0; it doesn't have a charge, but due to the mass differences that you can calculate from the product produced after the interaction with beryllium and the masses of the reactants, beryllium and helium, you can find out what the mass of the neutron is, and it turns out to be just a little bit higher than the mass of the proton, but they are roughly in the ballpark. And so this shows that yes, this is not only more massive than the electron, but it's roughly the same mass as the proton. And so that's the reason why you saw that you had about twice the mass than you did have number of protons, because you have about 1-to-1 amount of protons and neutrons, although that changes a little bit as the element gets bigger and bigger. Nowadays, the way we produce neutrons is through very intricate setups. Some of them, in China, some of them in Europe, some of them here. But we use very special machinery to create beams of neutrons that then we can use for various purposes. Alright, so with all of that information, we now have the key players that make up the atom: the electron, the proton, and the neutron. And the neutron plus the proton make up the nucleus of the atom. So in the next video, we'll talk about element notation and isotopes.